Light. We are moving on. Properties of light. So where we left off was the nuclear model with Rutherford that said the protons are in the middle, the protons and neutrons are in the nucleus, and you've got electrons floating around the outside. However, this was not a complete model. It didn't explain the location or the behavior of the electrons. As we learn more about this, we're going to find out that electrons are pretty much the reason that atoms do anything. Protons and neutrons, they're lame sauce. They got nothing on electrons. So, the wave nature of light. Light can be thought of as either a wave or particles. So, before the 1900s, it was believed that light was most similar to a wave. And so we, meaning scientists, discovered or came up with this idea of the electromagnetic radiation spectrum. Have you guys learned about that before? Have you learned about the electromagnetic spectrum, like radio waves, infrared, ultraviolet? Little bit. We didn't do a whole lot with it either, but we made posters because it was at the end of the 9th grade year, and I'm just lazy by that point. But that's neither here nor there. Crap, that recorded too. Lucky you, Kylie. So, electromagnetic radiation is a form of energy that exhibits wave-like behavior as it moves through space. That means it goes like moves like a wave. It moves through a vacuum at a constant speed. The sooner you commit this to memory, the easier your life will be. It is 3.0 times 10 to the 8th meters per second. So the electromagnetic spectrum is all forms of electromagnetic radiation. It starts down here with the radio waves. Radio waves have the longest wavelength. This upside down Y, it's a Greek letter called lambda. That is the scientifically accepted abbreviation for wavelength. And it moves through all the way up to gamma rays. Gamma rays then have the shortest wavelength. And here is our friend visible light. Visible light occupies an absolutely minuscule portion of this spectrum. Parts of a wave. Wavelength is the distance between two corresponding points on adjacent waves. So normally we call it from like crest to crest. The crest is the top of the waves. So right here would be the crest. And the bottom lowest point is the trough. The frequency talks about the number of cycles or complete waves that pass a certain point in a specific amount of time. The unit for this is cycles per second, better known as hertz, and not the car rental company. All right, so we have this lovely formula that says C equals wavelength times frequency. C is the speed of light. And what was the value of the speed of light? Meters per second. Very good. All right, so lovely little practice problem for that formula. The color orange within the visible light spectrum has a wavelength of about 620 nanometers. What is the frequency of orange light? So we have wavelength, the speed of light, and the frequency. It's asking us what the frequency is, the speed of light. Like I said, commit that one to memory. And our wavelength is 620 nanometers. Before we can use the formula, we have to do a little bit of pre-work. What pre-work needs to be done? Zoe? Nope, we leave it in scientific notation. We like scientific notation. Cora? Very good. We need to convert the nanometers to meters because the speed of light is in meters per second. So we take 620 nanometers, do our fun railroad tracks that we all have come to love. Oh, that was laced with sarcasm. And look on your half sheets or the pink sheets or the white sheets for your value of nano, and you find that it is 10 to the negative 9th or 6th? 9th. And when you calculate that out, these cancel, multiply across, you will get 6.20 times 10 to the 11th meters. Should that be negative 11th? Somebody check that, please. All right. This is negative 7th. Sorry, guys. So once we have this converted into meters, we can use our favorite little formula right now. 3 times 10 to the 8th meters per second equals 6.20 times 10 to the negative 7th times your wavelength. Divide it out. And what do we get here? Yeah, give me 2 decimal places. 4.84 hertz. Oh, no, times 10 to the 4.84 hertz. All right, any questions about how to work this formula? The key, I guess, is just to make sure your wavelength is in meters. You're going to have to probably convert a couple of those. So quantum physics, you'll either learn to love Max Planck or you'll hate him for developing quantum physics. He's from Germany. He's from German. Oh my goodness. He studied the emission of light by looking at hot objects, not people objects, like metal objects. He discovered that energy of a hot body, again, not an actual living body, just an object, could only be lost in small discrete units. Small discrete units is kind of redundant because discrete means small. So a quantum is the minimum quantity of energy that can either be lost or gained by an atom. So the formula that he came up with is E equals frequency times Planck's constant. Planck's constant is right here. The unit on Max Planck's constant, Js, is joules times seconds. And the unit joule is a unit of energy. Einstein, in 1905, he proposed that light could be described as quanta. And he thought that it behaved like a particle. He called these particles photons. These are particles of the electromagnetic radiation that has no mass. It has no mass because it is energy, not matter. And it carries a single quanta of energy. So, like with the bricks, it would be in a brick wall, one brick would be one quanta of the wall. Does that answer your question? It's not the nicest answer, I know, but okay, good. Yay, I needed that ego boost right there.